Okay, today, first of all, thank you to be here. Today we will see some possible exercises which I would like to say, similar exercise which you can find in the examination. Basically, we have seen also similar exercise, almost the same exercise during my, let me say, short seminars, no? This time, this semester. Okay, let me switch on the lateral camera and let me start with the first exercise. On this topic, we invested, no? We invested time. Go to, yeah. So, the idea to proceed is, as always, more or less, I try to explain uh, the meaning of the sense, uh, I mean, the direction in which we can proceed. Once I try to explain the configuration which I want to propose, and then I leave you some seconds, some 1 minute, let me say, and then I will propose the solution. Look, as we have seen in the lecture, we have, let me say, a coil, a rectangular coil. We have seen that this could be also a possible real application. Oh, I told you, I showed you, I think this valve which we used in the exhaust, better to say intake valve, but of course we simulated also for the exhaust valve of the cylinder, which in one design or in two designs, we had really rectangular, let me say, in the sense, if you consider the section, a rectangular coil with dimension B and dimension A divided 2. Why A divided 2? Because I am considering here, we can see here, two magnetic field, excuse me, I mix with German, two magnetic fields, uh, one in, let me say, positive direction, let me say, toward the my sheet, and the other one in the opposite direction. Also, this way to produce, this way to do this structure we have seen in application. I justify it, during the lecture. Let me go ahead with the exam exercise. Therefore, we have seen that the whole field is A. Therefore, A divided 2. We can see that the coil consists of 10 windings. As I told you, you don't need to use this value for the calculations. The values are there in order to be clear what we know. And then I will pose the questions. But in any case, we know the number of coils, excuse me, windings of one coil, the dimension of my coil, A and B, the resistance which I associate to the coil, the flux density B capitalized, we can distinguish B capitalized and B not capitalized, and the velocity with which, please pay attention, the coil is going inside the fields, or the field, if you like, constant. You remember the idea is you have to think that we have a force which compensate the back force. Well, we will discuss during when I propose the solution. Yeah, here, excuse me, a little bit confused, but the sense is in order to a better overview to discuss. Here we have some solution, because the question is not written here, but I did many exercises. The questions are, of course, the first question is graph the profile of the flux over time. Profile, I don't need to specify because we did just this kind of exercise. But in any case, this graph the flux phi over time and indicate the point in which, let me say, something changed. Let me formulate so roughly, but in the exam, the text, I will write probably a bit more precise, but what I intend, when we have something relevant to report, something changes. We can see here when we have these changes, and of course, in terms of amplitude. Think 10 seconds, 15 seconds, and then, or let me, this is a little bit stupid, 15 seconds. Think about 1 or 2 minutes, and then I will start with the solution. Why 2 minutes? Because the profile of the flux is one of the most important, probably the most important profile. I will stop now. I see a message in chat, but if you want to that I answer, please. Yeah, the audio is bad, but I don't know what I can do. I don't know what I can do. You can stop me also for question, because if I look to the paper, of course I cannot see your message. It is better now? I don't think so. It's a little bit better. Yeah. Thank you. I don't know if I can look in the risk. I'm looking for if I can find some option to improve, but the risk is it will be worse. I don't want to try to test, because it could be that the audio will disappear. But anyway, I didn't change anything. Yesterday the students didn't complain. Okay, if it's for you acceptable, let me go ahead. I stop now recording. Think 2 minutes or 3 minutes, and then we will proceed with the solution of the answer to the first question. We will see in 2 minutes, 3 minutes. Okay, look at the solution, and then we will discuss together. Yeah, why is going up easy? Because the flux, which is involved in the coil, is going up because the surface, the active surface, remember we called the active surface, is increasing. The second question is, why is going up linearly? Why it is linear, this change? Yeah, it's linear because the velocity is constant. We can see from here. I mean, if you remember the definition, you can find also this in the data sheet. The flux equals the flux density multiply the active surface. But the active surface is B, not capitalized, this dimension here, which multiply V, constant, multiply T. Why that? Because the movement is a uniform movement, which we have the velocity constant. Basically, V multiply T is the stroke, which I go over, let me say. This means it makes sense It makes sense. No? It makes sense. We can justify this profile. Now, what happens at time t1? Time t1. And time t1 is calculated here. Time t1 is the time in which these conductors, this here, basically reach this position. Because after this position, we have really something which changes. We can see from here. But in any case, what is this phi maximum? Phi m is phi maximum, the maximal value of the flux. The maximal value of the flux is basically, if you look at the calculation here, A divided 2 multiply B not capitalized multiply B capitalized. Why that? Because if you look at this equation here, B capitalized is here, fixed. You remember, B capitalized is the flux density. This depends on the material. It's an impermanent magnet, of course. I forgot to say, but during the lectures, I told you many times, it's a permanent magnet. B multiply S of t. We can see that the unique element we change is S. Therefore, the S of t. And this is B multiply V multiply T. B not capitalized multiply V multiply T. We can see that B capitalized remains. Why that? Because the maximal flux which we have is when the coil is totally inside. And we can see that A divided 2 is the same dimension as this plus part, let me say. This means in this particular case, we have that the geometric surface, we can see here B multiply A divided 2 at the geometric surface, corresponds with the maximal effective surface or active surface. Sometimes we call effective surface, sometimes active surface. Effective in the sense the surface which generates the flux. Because if S is equal to 0, anyway, effective is the concept, is the word which is related to the physical effect. I mean, can change over time an effective surface. This is the concept. The geometric surface is fixed. Now we have the maximal flux. In this particular case, please pay attention, just in this particular case, when the effective or active surface equals the geometric one. But in this particular case, because of the dimension. Now I'm going down because these conductors are here. Proceeding in this direction, let me say the right direction, I will include in the surface, in the geometric surface, a negative flux, because the second permanent magnet is oriented, the second permanent magnet is oriented in the different, let me say, direction. It's opposite direction, exactly. It's in the opposite direction. Now, the question is, this means that this effective surface, let me say, changes. Therefore, you can understand well the concept of effective surface. But what I would like to emphasize, or I would like to ask you, or I wonder, let me say, I wonder, this slope, why it seems to be not equal to this one? This is in particularity of this example. It's not equal because in this particular configuration, please pay attention, in this particular configuration, starting from point for the time t1, from the time t1, we have that on the right part, we include the negative flux, but on the left part, let me see, right here and left here, we exclude positive. I mean, at time t2, we have 0. Let me see if I made mistakes in this. No, I don't think so. It's okay. one second, yeah. In order to calculate more precisely, look, when we have this point T2, in which the flux is zero, when the surface, the geometric surface, is, let me say, in the middle. I don't know if you can figure out that half of the coil is in the negative part and half of the coil is in the positive part. But this happens in the time half of T1. I mean, better to say T2 minus T1, T2 minus T1 is half of T1. In this sense, what is T2? T2 is T1. Look here, T2 is T1 plus half T1. And this is the result. Look, T1 plus A divided 4V equal 3A multiplied 4V. It's clear how I calculate T1, no? This is easy. What is the stroke? Excuse me, the time. The time is the stroke, which I cover. I forgot to explain, but this is gymnasium. The time which I need to cover the stroke A with the velocity 2. I see something strange here. No, it's okay. It's okay because I made mistake now. I forgot that the stroke to be covered until T1 is A divided 2. Excuse me, is here. I didn't see. A divided 2 is the stroke which I have to calculate to cover in the time 1, which is A divided 2, the stroke divided the velocity. Do you remember, Gennaro? And here again, our question now. What is T2 in which we have the flux 0? Is this one, because we started from here, plus this time here, which is half T1. This means A divided 2V plus A divided 4V, which make 3A divided 4V. I don't know if it's visible. I don't know if I have something more explicit, but no, I don't have, but it's easy to see. No, again, A divided 2V plus A divided 4V equal this one. Try to do at all. T3. When we have the maximum negative. But when we have the maximum negative, as before, when the geometric coil is totally in the, let me say, negative part of the flux. This means again minus phi m. This is we can justify very well because it's the same B, but the same our effective surface, which equals in this particular case the geometric surface. What about T3? It's the same. In the same sense, the idea is the same. T2 plus half of T1, this element here, equals this element here. Intuitive, no? And A divided V. Why that? Because T2 is this one. If I add plus half of T1 is A divided 4V. The denominator is the same. 3A plus A equals 4A. This means I can cancel 4 and 4. I have A divided V. The rest is easy because we have exactly the exit phase, which have the same slope as here, because of the symmetry of the system. We are at time T3 and this position here in which the whole effective surface which equals at this point, at the point T3, as at the point T1, they are just in these 2 points, the effective surface equals the geometric surface. We start from here the exit phase, But of course, the law is always the same, the law, yeah, the law, why not? But I am going to 0 here. In this phase, we are going up here. Of course, we are going to 0 because we are negative. Try to imagine, I'm going out. This means I exclude negative permanent, negative flux, let me say. What about T4? We can see here is again T3 plus this time, which is equal to 1. Because I told you, I tried to explain that the entry phase equals in the sense, reflect the exit phase. Again, the exercise in the exam must be done intuitively. You don't need, as in the lecture, as in the first lecture, to calculate exactly this line, the equation of these lines. You remember, we have a lecture in which I did complicated thing in order to show you ones, which we can be also precise, but you don't need. The idea is to understand the concept, to draw graph correctly with explanation, calculating the time which something, let me say, in which something happens, something relevant happens. Yeah, again, T4 plus half T1 is A divided V, excuse me, plus T1, excuse me, I made a mistake now. T3 plus T1 is exactly T4 because this time here is equal to 1. This means A divided V plus A divided 2V. And of course, do you remember 1 divided 2 plus 1 is equal 3 divided 2. Of course, A divided B. Multiply A divided B. Try to do at all. Now, we have some other questions to be answered, but a couple of them are extremely easy. Because the second typical question is, please calculate the induced voltage. Meaning, when the coil is going inside, do you remember the Lenz effect and so on? We have a voltage, the name is induced voltage, which appeared, let me say, in the coil, is induced in the coil. And we can see here, you can find also this equation here in the data sheet. It's enough. Why that? Because we can see this U induced is minus n, the derivative of the flux with respect to the time. Of course, the derivative in this case is easy to do because in a linear system, the derivative is extremely easy. Practically, we can do also a little bit more precise, but practically means this distance, or this distance, V m, if I want to consider the derivative of this part here, because the velocity is constant, the phi is in a linear, but this is the slope of phi over time, of the slope. This divided this. Of course, then I have to multiply by minus n. And we can see here, this level here is minus n. Yeah, is the explanation here is minus n, multiply B not capitalized, B capitalized, multiply V, because is phi maximum, which is this one, divided T1. And you can see that A divided 2 I can cancel. No? Again, phi maximum is this distance. T1 is this one, A divided 2. This means A divided 2, I can cancel. This means 2n, excuse me, n, because A2, I can cancel with this. N minus n, no? Multiply B not capitalized, multiply B capitalized, multiply V. Why V here? Because please pay attention, this divided this, A divided 2, I can cancel. But I have here B not capitalized, B capitalized, divided 1 divided V. This means I multiply by V. Of course, minus N. As I told you, you don't need to do the calculations. Absolutely. The values are there in order to be clear what is known. No? And then I will pose these questions. The first question, the flux, the second question, induced voltage. What happens here? Happens that we have twice the change. The change is, or better to say, delta phi. I don't need to try it in this form because we have a linear function. Remember, the slope is constant. Twice m is the change, divided, we can see here, T3 minus T1. T3 minus T1, this change. But T3 minus T1 is T1. Remember, I told you before. Is here the explanation. I think, let me see. No, excuse me. This is the explanation for this. This is we don't need to explain because it's twice. What is it? Twice this is it twice his, but positive, no? Because he has, let me say, in a positive slope with negative. Where is this? Is the derivative? Yes, negative slope with a minus is this one, but twice. I told you also at the beginning intuitively twice slope, of course, negative. But why is twice? Because this time here is equal to this time here. But what changed is the changes of the change, which is twice the change which we have before. What about this induced voltage due to this flux? Where is exactly as before, no? Because you remember I told you intuitively, not only intuitively, that the slope is the same. This slope is equal to this slope. Basically, this changes, or that this change over this. But it is exactly as before. Okay, to calculate the current, no problem, because it is enough in accordance with the model which I presented. I didn't consider the inductance. If I consider the inductance, it's complicated. Remember the letter. I have to divide. If the question is graph the current, it is a question. I have to divide this graph here by R. This means I have to just to copy this here, and please don't forget to divide by R. No? Ohm law. This is the unjust current which is generated by this unjust voltage. The shape is the same. It's twice, but anyway, I have to divide by R this graph here with the corresponding value. We can see that we have this element here divided by R, this element here divided by R. No problems to calculate or to graph the current or unjust current. Please pay attention now. Calculate the electrical power. This is easy. A little bit more complicated is calculate the mean value of the electrical power. Both as important in the design and the analysis of an actuator, but more important is the mean value. As always, I would like to say. Over time, it's important because sometimes we have also some constraint in the amplitude. But the mean value is more important because, let me say, it's the status of the thermal status, correspond to the thermal status of the actuator. Because we know that the power is related to the temperature. And the problem in the actuators, in the machines, is always the temperature. How we can anticipate the temperature, let me say. Okay, to draw PL of T, no problem. It's U induced divided R, for instance, or R multiply current square. We have this. Basically, I will consider, if you want to apply this, the induced voltage square. You remember the induced voltage was at the beginning here minus NB, not capitalized, B capitalized at the beginning in this interval. B capitalized multiply V, I have to square, this means becomes positive, divided R in accordance to this Ohm law. And of course, here, why is 4 times? Because between T1 and T3, I don't know if you remember, otherwise I showed you, we have it twice. If I square this, I have a 4. 4 times this. Everything is the same, U squared divided R, but 4 because we have a factor 2 in the voltage. And this level here is exactly this because we are exactly the same voltage, induced voltage. Very important now, think 1 minute, how I can calculate P max, P medium is here. You remember in the lecture I did once, or probably just once or twice, applying the definitions from math. And then nevertheless, I told you 2 or 3 times how we can calculate a little bit quickly, but if you don't want to apply this quick method, this is always something which can be applied. Think 1 minute, and then I will give you the solution. Then we are almost ready with this kind of exercise. Let me see what I have to tell you. No, we have a little bit more, but it's not much. Oh, let me see. Yeah, think 1 minute. Okay, let me show you the solution. Look at this. Is a rapid way to calculate the mean value. How we can justify this? This short form to calculate the mean value. Look, I put here 1, 2, 3, 4, 5, 6 surfaces. Why surfaces? Because if you remember in gymnasium, the mean value, if you consider, let me say, this expression here, which reflects the mean value, which is the mean value, this means, remember the meaning, first of all, the meaning of the integral. The meaning of one of the meaning of the integral is the surface. Now, this expression here, if I divide it by t in general, in our case, t, which I am considering is this t4 for the whole time interval. No? In the exam, probably I will write a little bit better, but we did always, so it makes sense to consider. Otherwise, if you want to consider until here, you have to write until when, but makes sense. Makes sense because our phenomenon is interesting until T4. I told you why T4 is the time which we finished with the exit phase. You remember? Do you remember the question? The relevant points with something happens. This means for us it's the relevant bit T4. This means this T, which is the general definition, is in our case T4. Now, the meaning is to find in a line, let me say in a line, on a rectangular surface, which is equivalent to this, excuse me, 6 surfaces, something like, and the surface under this mean value, this line, equals the sum of these 6 surfaces. This means, why this calculation? Look at this. we have this element here, or this value here, which is this level. It's clear. I explained quickly, but we have seen many times during the lecture. I will insist again. This value here is this level here, which from which I consider this constant line, the power. From time 0 to time t1, we have this value here. This means this. Multiply t1 is the surface 1. But if you look here, I was clever, let me say clever, to divide the whole surface with 6 in 6 surfaces equals 6. They are all equals. We can, you can believe me intuitively. If you want, I can calculate, but it's visible. Because t3 minus t1 is equal to t1, t4 minus t3 is equal to t1. This level here is twice this level here, because we can see that I can divide it in 4 parts, 1, 2, 3, 4. This means this multiply t1 is the surface, as I told you, of one element. Multiply 6 is the whole surface, but the whole surface divided 1, 2, 3, t1 equal t4, which is our t. I mean, the integral from 0 to t, which is t4 in our case, is this. In our representation, divided t4, which is 3 divided 3 multiplied t1. This is t4, this is t4. If you don't like this method, apply the definition. We have seen, I think, 1 or 2 times. No, probably 3 times, because I did 3 cases in which I will calculate exactly the integral. This is an exercise from math, and then we obtain this. Look at the last question of this exercise. I don't want this. But anyway, it's so easy, I can show you. Draw the force, the brake force. Remember, we have a brake current. The unjust current. Here on the brake force. Why this? Look at this. In the data sheet, in the Formelsammlung, we have the induced current multiply N, multiply B, not capitalized, multiply B capitalized. Of course, we have to know that the force is the brake force. If you look at the current, it seems to be something strange. In fact, we have to be careful to be more precise here. I have to consider how possible to say the absolute value, if you consider this brake concept, the absolute value of the current. Very often we write directly so, but we have to remember that's in the brake force. Of course, because of this is the brake current, even though change the sign, but you remember I explained when the sign change of the current, change also the sign of the flux. But here we cannot see. This means, to be precise, should be, but it's small. It's very often we didn't write this absolute value in order to calculate the amplitude, because we know from the lab this is the brake force. But applying this, it's basically easy to do that, because you know the induced current. Please pay attention, positive. In this sense, I forgot to say, yeah, if I put this, I have to put minus. No? Otherwise, very often we say brake. Now we can see a brake force without any notation. This means it's negative. You apply it. Minus the absolute value of the current, multiply N, multiply B capitalized. Easy. Because the current was, you remember, this n b not capitalized multiplied b capitalized squared divided r. This was the current. No, excuse me, was stupid, made mistakes. I have to look. It's not exactly this. Otherwise, that doesn't. This does not work. Was n multiply b capitalized multiply v. Then I have to multiply by n multiply b not capitalized multiply b capitalized. This means the current was this. Excuse me. Yeah, exactly what I am showing without square. Makes sense. Otherwise, I have to look. I have to look. It was this expression without square. Of course, I have to put. Mm, yeah, so we can write so, or better to say as before, Breakford is exactly this without square. Let me look. And then if I multiply by n b not capitalized, b capitalized, I have a square this part here. Let me see if I find, so I am more precise, but I'm sure about that. Yeah, found it. Yeah, in fact, in this part here, as I told you, we have n b not capitalized, b capitalized, v divided r. And then I have to multiply by n b not capitalized, multiply b capitalized. Therefore, we have this square. Probably before what more precise. No, I write this form of a break means it's in any case negative. Yeah, and this here now we learn is 4 times. This 4 times we can see in different form. We have to be careful in this sense because we have, you remember the contribution left and right of the current, but to avoid mistakes, look at this. This also can help to graph the force. Why that? Because the electrical power plus the mechanical power must be zero, no? Because in our system we have just two energy or two powers, two energies of two powers plays in a role. Let me say, if I am moving, I transform mechanical energy into electrical one. The mechanical power, if you remember in another courses or by my lecture, is induced force, which is force which I clarified before. The break is the break force, which is induced. Multiply the velocity. No? But in order to calculate now the V induced is P electric, let me write. I'm looking for this break force. This is the break force. P electric divided D, right? Divided D. Probably this is the direct way to calculate this break force, P electric over time. I cannot write. From if I combine these two expressions, no? And then look, P electric, we have it. Minus, this means I have to consider the symmetric curve with respect to this axis. And I have to divide by velocity. This means I have to cancel the square of the velocity. Excuse me, here and here. And you can see. I put out, let me say so, from the square v, because I cancel square, but just for v. This means that this expression here, or this graph here, with their calculations, are exactly equal this one, but symmetric with respect to the time axis. And I have to consider V outside of the parentheses because I have to cancel the square because of this principle. This is the principle, no? This is the principle. And this is the definition of the mechanical power. I think this idea I would like to suggest in order to graph this. Sometimes I am asking also the generated power, no? The mechanical, no? The mechanical. The electrical I already asked. Okay, we stop for a cup of tea, 3 minutes, and then we will go ahead. We will see in 3 minutes. Okay, I would like to propose another exercise of this topic here. I would like to accelerate a little bit. Let me see if I am. I would like to accelerate a little bit. And then, of course, we will proceed with another exercise. Look at this. Same questions. Graph, flux, just voltage, current, power, calculate the mean value of the power, calculate the break force, and their relevant points. Look at the scheme. Quite similar as before, but in between, we have A divided 2. As in a region without, fields. As I told you, this is in a real case, which, I mean, we can find this also in possible applications. Remember, I told you. Now, let me a little bit do concretely the exercise without repeating theoretical aspects. Look, why that? Why I'm going up as before? I mean, we don't change the entry phase. Why is constant? This is a little bit to be analyzed, but it's absolutely not a problem. Why that? Because we have the maximal flux with the same value as before. Where I calculated? I didn't put, no, I put it, yeah. Even though now we don't have A divided 2, but the surface, this effective surface, is determined by this. Remember this in the first lecture I clarified how we can because it's the minimum length between this and this. Do you remember? If you look at the first lecture, the exercise, I clarify more precisely this. Why is constant? Because when this conductor is here, I am moving left, right, excuse me, the effective surface does not change. T1 is as before, I don't need to explain. What about T2? T2 is again as before T1 plus T1, again, now I cannot say again because the phenomenon is a little bit different, but again, the sense, the value, but for different reasons. T2 is T1 plus T1 divided 2. Therefore, is this one? Let me see. Yeah, it's correct. Oh, let me see. Let me think. We will probably go too fast. No, I made a mistake, excuse me. It says before the sense of T3. Let me, not this one here, the T3, the example before. Let me do in this case, otherwise. Why remain constant? Because, first of all, because when I have with this conductor here, I go right, remain constant because this effective surface does not change. Why that? Because half of the geometric surface is outside. This means moving and moving. I don't know if it's possible to see. You can see that if you think about this, half part of the geometrical surface is outside, moving on the right, remain constant until here. What is the time? It's exactly T1. Excuse me for the mistake before. I mean, T2 minus T1 is T1. This means T2 is 2 times T1. Excuse me for the mistake before. In the sense, I thought about T3 of the example before. T2 is 2 times T1. Because I have to cover the same surface, I mean, or the same stroke. Yeah, I covered until here. When these conductors are here, I cover A divided 2. To achieve or to reach this, I have to cover again A divided 2. This means I need the same time to cover the same velocity. Then I am going down, but as before, with a slope twice, because for the right part, you remember the concept, I including, let me say, negative flux. For the left part, I have excluding positive. We discussed a lot in the lecture. Or if you don't like this concept, try to calculate T3. When we have T3 in the middle, we have something in the middle which don't generate or don't give a contribution in terms of flux. Then we have right minus and left plus. This means 0. When this happens, this interval is half of this interval here. It's intuitive, and you can calculate with this concept. T3 is T2 plus T1 divided 2. And we have this. Try to do it. The rest from here basically is in a profile symmetric with respect to this point here. Why that? Because we are exactly in the middle in a symmetric situation. I mean, if you want, we have a pre-exit phase, because you remember the exit phase was defined in the last step, let me say. But if you want to introduce another definition, we have a pre-exit phase starting from here. But just to understand what I intend with this symmetric part. This means now it's easy to justify this value here, which is minus this one. Constant. When we have the constant, when this element here as here, but these conductors here is here. Here we have the time T4, because moving out, not exactly the exit phase which we called in our definition, but remain constant because we have a part of the geometrical surface which is not involved in the flux. This means moving right, we have this effective surface which is moving, please pay attention, inside the geometric surface. Then when these conductors are here, we have T5, and we start with the exact exit phase. Try to do at home to calculate as before T5 and T6, but I explain how we can do it. In just voltage, now we know minus n, the derivative, and the derivative can calculate it, for instance, here, this distance divided this distance here. Of course, minus. No? Look, why here we have it twice? As before, I told you intuitively, not all intuitively. If you look at this T3, if you calculate this T3, we can understand very well that the slope is twice. You remember, from the right, I include minus, from the left, I exclude plus, the same concept, but if you don't want to apply this, you can calculate this T3, and we can see mathematically that we have twice the slope. What is this derivative of this slope? This here, as before, this is twice this here. But this time, as before, is the same like this one. This means the derivative twice. This means these two here, and this is the graph. Then, current, no problem. The same graph, but of course, please divide it by R. Exactly this divided by R, no problems. Because we model this coil. We model the coil, excuse me, just with the resistance. Power. The mean value of the power. I don't have any higher here. Let me show you the power. Why this one? Again, voltage square divided R. I don't need to clarify this. No? This picture here, positive, up to 2 is already positive, up to 2, therefore this 4, 0 remains 0. No? Please pay attention. Why 0? I didn't clarify, but it's clear, because we don't have changes. We don't have induced voltage. The derivative is 0. You know, I don't have to comment this. 0. In fact, we can see also here. Probably not this one. 1 second. This is mistakes. It's not exactly the exercise. 1 second. 1 second. Yeah, excuse me. This is another exercise. Yeah. Page number 2. Yeah, good. Yeah, makes sense, no? Because we have 0. Power must be 0. Because this was another exercise. Because the voltage, induced voltage is 0. I clarified 0 because no changes in flux. No changes in flux, the induced voltage is 0. I consider the voltage and I square. No? Therefore, 4 times. No? Everything squared means 4 multiply everything which we have here squared. No? 0, 0 power. Yes, positive is positive. Everything squared. Easy as before. Excuse me for the mistake. We have the page number 2. This was the page number 2, but for another exercise. I think what the exercise as before, something like that. No, different exercise. The rest not change. But look now what I put here to calculate quickly without using the integral. But you can use the integral if you don't like this way to proceed. This is a way to proceed. I think in gymnasium, that is sometimes, but it's an integral basically. Isn't an integral. I told you 3 times with the integral, but also I try to divide the surface in equal parts, unitary, let me say, surfaces. And now, as before, we have also here 6 active surface. Let me say in this form. This means this is the amplitude. This distance here, let me say geometrically, multiply T1, because all elements which I am considering this representation, T1, this is T1, this is T1, this is T1 in particular when this is active, no? Very important that this is T1, this difference is T1, this difference is T1. I explain quickly, but I explain. This means the amplitude multiplied the base is the surface, unitary surface. We have 6 surfaces. or let me say active surface, in which we have the voltage, not zero. And then I have to divide by T6. But T6 is 5 times T1. 1, 2, 3, 4, 5. This is a way to calculate the mean value. Of course, if you don't like, apply the integral. I told you 3 times, but now we expert here. What about the force? No problem in brake force. Look at this. I would like, if I would like to suggest, I would like to suggest to use this. Look, F in just is minus P electrical divided V. This means you consider this graph, you do the symmetry with respect to the time. You can see this symmetry with respect to this axis. Excuse me. These two representations, these two graphs are symmetry of this axis here. With respect to this axis here. And then I have to divide it by V in order to have the amplitude. Because of this, no? Because of, let me say, of this expression. I mean, this is the conservation of power or energy. This is definition of mechanical energy. I can, this is the conservation of energy. This is the definition of the mechanical energy. I plug in, I have this one. This means in our case, the brake phase is minus P electrical divided V. P electrical, the information of P electrical is here. And this exactly symmetric with respect to this axis because of this minus. And V is outside of the parentheses because I have to divide this expression by V. It was a little bit faster, but I think it's enough. Okay, I will upload everything. You can find also another exercise, which I don't do now because I will leave, but it's similar. Now we understood what is the trick. It's similar, in this sense, it's similar. We have to think a little bit what happens, but I don't want to do another one. Let me do another kind of exercise that can appear also in the exam. Let me see, because here I am so confused with the material. Therefore, I took the wrong page number 2. Yeah, this one. It's full. Okay, look here. Possible question. I will give you these equations. You will receive this equation, which is, you remember, I discussed a lot about the model, how these 3 equations come from. We introduced the 3 equations using the voice coil motor, or the actuator, better to say. It's complex because we included here the inductance, and we included here the mass of the coil. You remember at the beginning, also today, we started with something really extremely particular. The velocity is constant, the current is piecewise constant. This means, yeah, the acceleration is 0, and we collapse this in equations very easy. And also, the derivative of the current is 0. If you look at the first equation here, we collapse this in the basically in an it's an ohmic equation. Exactly what we did until now. But of course, if the velocity is not 0, excuse me, it's not constant, this means we have an acceleration. The acceleration is something connected with the mass. I mean, in the Newton balance, and also in the Kirchhoff balance. In this case, if the movement or the velocity is not constant, you remember when I sketched the solution, or what happens if these inertial aspects, let me say, considered. This means we have an induced voltage which is not stepwise constant, because you see here the induced voltage depends of the velocity. But if the velocity is not constant, the induced voltage is not constant. We cannot say that the current is constant or stepwise constant. Anyway, it's not exactly constant because the structure of the magnetic fields generate in stepwise constant, nevertheless, induced voltage in induced and just current, but somehow constant even though stepwise. This means everything changes. You have to consider also the inductance. The question is, graph of the system here, of this three equation, the block diagram structure. I give you 1 minute and then I come back. Now, how we can justify this kind of scheme? It's extremely easy. I would like to start from here, from the goal, a possible goal. But if you like, you can start from here. Once I told you that I show you how we can nevertheless start from this point here. I don't know what you prefer, but in my opinion, it's easy to start from x. Why that? Because look, this equation is extremely easy to be represented using this language here. The derivative of the position, x is the position. No? I don't need to express or to justify or to clarify the elements here. We know the derivative of the position is equal to the velocity. This means the integral of the velocity is equal to the position, assuming that I know the initial condition of the position. I told you many times, if you remember in high school, this means between velocity and position, we have an integral. And of course, I have to assume that I know the initial condition. This could be also in some graphical tool like Simulink and so on, very well understand. Then, here we have the voltage. But look at this equation here. I am considering the mechanical system. Let me see. This equation here is in a relation between the derivative of the velocity, many other things. This means the derivative of the velocity acceleration. But as before, between velocity and acceleration, we have an integral. This means if I know the initial condition of the velocity, I can represent the relationship between velocity and acceleration in this form. As before, which I did between position and velocity. Easy. Therefore, I would like to suggest to start from here, because immediately after two integral, you have the acceleration, which is here. But if you have the acceleration here, look here. Now, it is easy to represent in accordance, which I told you during the semester, the new language, which is the language of the block diagrams. Language is the mathematical language, well, which came from a physical description. Plus, minus, plus. Why that? Because we have plus, minus, plus elements. Here, immediately, we have an external signal and a low one, for instance, you remember, of the actuator, divided by m, or f0 multiplied by 1 divided m, generate or represent, better to say, this element here. What about this? Minus, we can see here, excuse me, minus, we can see here, v velocity, which is the same velocity which is here. It's the same, because the equation is the same, because it's called with the same name. About more clarification, you have to look at the other video, but v multiply 1 divided m. So I forget kf here. Excuse me. Now, v multiply kf divided m with minus, excuse me for this kf. We have this one. Then we have this component here, which is the motoric force. Or let me say, could be also brake force. It depends. No? I told you a little bit. Depends on the sign of the current. But in any case, the expression is exactly the numerator which we have here is exactly, do you remember, the force which we have seen as motoric force, but also as brake force. Depends of the sign of this. It's exactly B capitalized multiply B not capitalized multiply N, divided M here because M considers the acceleration. But here it's the Lorentz effect. I mean, if I remember the voltage in input, like here, this current here is the sum of the current generated, let me say, by the input and the brake current. And in this balance here depends what is the higher component in order to establish if it's the motoric force, this here, the numerator is the motoric force or the brake force. In this balance depends of the current of the sign of this. The phenomena which I explained before, we don't have the input, U input, because otherwise a little bit more complicated. Therefore, was necessary in a brake force. Here it depends with respect of this balance here, if dominate the current of the input generated by the input through this dynamics, because the dynamic of the current here, or dominate the brake effect. The brake effect is here. We can see minus plus, minus plus, minus plus. Depends which of both dominates. But we don't have to do so deep in the exam. What happens here? It happens that I try to represent these dynamics here with this new language, but is it similar what we did for the mechanical? Look, here we have the current, because the current should be multiplied by this element here to obtain the force, could be motoric, could be brake, divided M. You can see here. Now, between the current and its derivative, why I'm calling, now I'm looking for the derivative, because here the dynamics is represented by the derivative. We have an integral. Again, we have to know the initial value of the current. Then plus minus minus, why that? Because you have a plus here, minus minus. This means U input divided L represents this element here. We have an input, the voltage. Could be the output of the controller, we will see next semester. Minus minus, let me consider this, for instance. Minus B capitalized multiply B not capitalized multiply N divided L multiply V is represented here, is exactly this induced voltage, at least the numerator, the numerator. We generate, remember, the brake force somehow, because generate an induced voltage, then depends which dominator both. I try to explain also in the lecture. And why this minus here, which is multiplied by current and RL, because I have to represent this. The current is the same, as before, the velocity is the same. Excuse me, here, probably you didn't see this. This was the induced the velocity we generate thanks to the product of the numerator, B capitalized, B not capitalized, and the induced voltage. Of course, divided L, because in this representation, we want to look at the dynamics. We will see next semester why. Again, the concept, you don't have to write. It depends which of both dominates. To have, if dominate this, the motoric force. If dominate this, the brake force. In the example which I told you was extremely simplified, in which we don't have this. Think about this. Try to do at home. try to do also different examples from the material which you can find in my study. I will upload everything. Let me now show you the solution to another question. Sometimes I will upload everything. I ask to write in matrix form this information here. But it's easy. You put matrix in vector form. You put it in a vector. This element, you can see here. The derivative, we say derivative of the states, the derivative of the current, the derivative of the position, the derivative of the velocity, should be equals the matrix A, which multiply the vector x, this time without derivative, because we don't have on the right part the derivative. We have just in the left part. Plus the vector of which represent the map of the input, multiply the u input. And then eventually disturbances. The map of the disturbances, we will clarify the word map now, multiply the signal of the disturbance. Look, here is easy to build, because you know that the input appears just in the first equation. 1 divided L multiply U input. 1 divided L multiply U input. In the first line and the first element of this vector. The first element of this vector. Both are 0 here. Why this matrix, why this matrix is so complex? It's not complex, because if you remember in math, row multiply column, row multiply column, row multiply column, through this example, through this rule, you can build or can rebuild or can justify this expression here. I mean, these two languages, this matrix language and this here must present or must be reflect the same system in this sense. Considering D, now we clarify A. Consider this easy because similar to the input, the input appear in the first equation, the disturbance, the load of the actuator appear in the equation number 3, therefore 0, 0, 1 divided 10, you can see here. Yeah, probably, excuse me, the example is not this one. Yeah, but it was calculated before. The scheme is as before. Excuse me, where I put it? It's difficult to find now. Do you remember I told you I cannot find now, but it's the example as before. No, it's not this. This is another example. I will upload this. But the example was, yes, we don't have F0. We can see here. We don't have F0 here. I don't know where it is. Now here's too many slides. I cannot find the shape. But it is like as before. Excuse me, I cannot find where I put it. But it's the exact, probably here. No, it's not here. I cannot find. I don't know where it is. And it's here. You can see this. In this matrix we have the example. Let me clarify this. Do you remember row multiply column? Row multiply column. I have this multiply this, plus 0 multiply this, plus this multiply this, plus this multiply this, plus 0 should be equivalent to this expression. if you remember in math, because you did the mathematics in math, row multiply column will generate exactly this. This means, oh, again, this equation. What about this equation here? It's easy, because if you consider the matrix 0, 0, 1, 0, 0, 1, if you multiply by current, 0 by current is 0, 0 by position is 0, everything plus, no? 0 multiply this plus, 0 multiply this plus, 0 multiply this plus 0 multiply this plus 1 multiply v, we generate that. Yeah, we represent, better to say this. Try to do at home. This is the same. Row multiply column, you will obtain row multiply column. We will get exactly the states which are present also here. Of course, please pay attention to this. The disturbance in this case came because we have a plus plus, we have a here 0 multiply u input, because u input is not directly involved in the mechanical system, plus f0 divided m. Okay, let me go ahead. Another kind of exercise which you can find in the exam. Now, you have to be careful, don't mix the slide because it's extremely. Yes. Look at this. Given the actor in one, the actor in one is characterized by this. The same. Yeah, the same. This is the actor. Please draw position, velocity, and current in the following cases. To remember these cases. Kf equals 0, or very small, r not 0. Kf not 0, but r very small of 0. Kf equals 0, r equals 0. First of all, why it's interesting or important to analyze these three cases? Of course, in case of the constant, in case of constant voltage, you input, for instance, equal 12. Very important concept. It's interesting because very often, not all, but it could happen that we try to reduce the friction. Remember, this is the friction. Why that? Because the friction basically are losses. There's losses. No? Another case, for instance, could be interesting to reduce, to analyze the resistance very small. Of course, mathematically I put 0, but of course that is not possible. No? Just an ideal in the case, in order to be analyzed, it practically means small kf, small r, 0 is not possible, or at least in the real condition. Or both 0, also in this case, in the theoretical part, because again, 0 is not possible. You remember how we did? Think 30 seconds about the first example. Please keep in mind Kf equals 0. This means this loop is broken. We don't have any connection here. Kf equals 0. Think 1 minute and then we will proceed. About this case here. The mechanical loop in which Kf is involved is broken. This means no feedback, no losses. Okay, okay, this is the solution. It's a little bit organized, strange, but I think this is the solution. Yeah. Look, here is in vertical, we have the we have the solution. In order to interpret these three graphs, in order to be able to reproduce, I think we can start, I would like to say, analyzing the scheme. And in particular, I would like to consider this current here. Why I would like to start with the current? Because the current is the cause of the velocity and then of the position. But of course, could be a similar analysis, could be done in a different way in a similar analysis. But in my opinion, we can understand better everything if you try to interpret this. Starting from zero. Why starting from zero? Assuming that no magnetic field inside, no current. I put the voltage, of course, the current, the U imp, 12 volts. Remember, it's written here, 12 volts, and a constant. The current is streaming inside. Look, but the current does not converge to a constant value, even though, I mean, converge to a constant value, but converge to zero, even though the voltage is not zero. Why is converging to zero? Yeah, it's interesting because if you look here, of course, this is not included. No? This is not included in the analysis. Even though it does not change much, but we will change the output. But conceptually, for the current does not change. Why is it going to zero? Because look at the scheme. Please don't consider this is more easy to see. Here we don't have loss. Also, with this input, with this disturbance, which is an input, an accessible input, we don't have disturbance. This means, excuse me, losses. This means for the current does not change anything, but change the voltage, excuse me, the velocity and the position because we have a disturbance. This means does not change the current, nevertheless, the presence of this. Please consider without this. It happens now that here we don't have losses. With or without this. Don't consider the disturbance. This means the velocity will increase, the acceleration change, but look, because of the presence of this feedback, which is a negative feedback, the system, do you remember, we have learned using this example at the beginning that the system reacts with a negative voltage, induced voltage, Lenz effect. We nevertheless try to reduce the current because we have an input plus, but we have a negative contribution and a negative contribution here. But very important is this negative contribution. Why that? Because the velocity is increasing. The velocity is increasing very strongly. We don't have losses here. Let me say very strongly just to understand. But there is a point. There is a point. Increases. This contribution, of course, together with this, but this is not relevant. I clarify this. If this is relevant, will be equal to this signal here. This means no changes in the current. But no changes in the current does not mean zero. But of course, we can understand here that it could happen that this velocity will be really high. What means that can generate a signal larger than this plus. Why that? Because here we don't have losses. I try to explain intuitively. To be more precise, we have to solve the differential equations. But believe me, it's intuitive. Now I clarify more, a little bit more, thinking that once we overcome the inertia, let me say, or better to say, if you look here, I told you this is zero. Huh? If you remember, we have this side divided in continuity, we have this equation. We can see that the derivative depends directly on the current. But of course, because of this limitation, the current is also limited. And not only limited, is going to zero because, think about this concept here, because we don't need electrical energy to be transformed in mechanical one to maintain a velocity which compensate the input, because we don't have here losses. Because of this feedback here, we try nevertheless to limit the current, the derivative of the current, because here we have zero, but we could also negative. We can see here, because here, of course, we can increase a lot. The derivative is negative. But the real reason we have a velocity not zero, we can see from here, steady state, but the current zero. It seems to be a contradiction, but it's not, because here we don't need energy to sustain the movement, because we don't have losses. It's in a particular case in which this product here, with me a minus, and this element here, steady state, will be equal to this one. But until, anyway, for all time, this two element is larger than this one. So this is negative. The derivative negative means I will decrease, but the reason is I don't need energy to sustain electrical energy to sustain the movement, the mechanical movement. What happens here? And here, of course, you can find, you remember the asymptotical velocity because yeah, asymptotical means the current is zero, the derivative is zero from the first equation. The derivative is zero, I told you, the current is zero, I try to explain. Of course, to be precise, I have to solve the differential equation. I don't want to do. And of course, now the final velocity, steady state, therefore I put infinite, is you input divided B capitalized, B not capitalized, divided N. What happens now Kf is not zero, but R is zero. Again, look here. Why now we have a current which is not zero? Yeah. Because here we have losses. Here we have an input. Here we have a feedback. But the current is not zero because we have an input in terms of voltage. The energy will transform in the electrical energy will transform in mechanical one, but we need nevertheless always electrical energy to compensate the mechanical losses. It's not the case as before, in which we have nevertheless an input, constant, very important, constant input is there, the input is there. To transform this electrical energy in mechanical one, there is a point which I don't need anymore because the system here before we don't have losses. Now we have losses. This means this transformation is still there. Because in order to, or you can think that the velocity we will achieve is less than before. Try to calculate, but also this is not so difficult to be calculated. You have to consider this equation and this equation, which this is zero, but a little bit more complicated because we have two variables, no? The current and the velocity, but two variable, two equation. This is not there. We can see this is not zero. Try to do. And then the integral of the velocity, this one here I didn't clarify, but of course, if going to the constant, this going to the ramp. If the velocity is going to the constant, the system remains stable, asymptotically stable, because I mean, with respect to the velocity, of course. I mean, we converge to the constant, let me say so. Because nevertheless, in both cases, we have losses. What happens if no losses? Yeah, this is a little bit more difficult, but we did. If no losses, we have oscillating variable. The current is positive, negative, positive, negative. Because of this feedback here, as I told you before. We oscillate in terms of current, we oscillate in terms of velocity, but of course the velocity is a particular oscillation because the mean value of the velocity is not zero because the motor will run, but we can see that we have an acceleration which is also sinusoidal, or the cosinusoidal. Here's the position, which is going ahead, but with these oscillations. Why the current nevertheless is positive, is negative, is positive, is negative? Yeah, why? The reason is the energy from electrical goes in mechanical, and from mechanical coming back totally as an electrical. We don't have losses. Therefore, positive, I give energy to the system, and the system give the same energy to an input. Input, I mean, the electric, let me express in this form here. The electrical system transfer the energy to the mechanical one. This means we will move in this particular form. The velocity state, how are we moving? But why this positive is negative? Again, because the electrical energy will transferred into mechanical, but we don't have losses here. We don't have losses here. The same energy is coming back. Of course, to justify perfectly the curves, we have to solve the differential equation with these conditions. We will do in the course of dynamical systems. But intuitively, you can look at home at this page, and now I will upload again. I will upload let me say the slides and also the presentation. Let me told you 10 minutes, and then we will conclude about the third possible example. But please do at home all the exercise you can find in my study. A possible exercise is this one, which I show you two exercises. One a little bit easier, one a little bit more complex, but not complex that you cannot do. Let me show you this. It's Moses here. Easy. Oh, one second. You can find also, this is my study. Again, we will see on Monday evening. It's a shame 20 hours I will communicate per my study, because I have a tutorial with another course at this period. Is really for me is extremely difficult to because we have also deadline for project, but of course you have priority. My priority for you. Therefore, today we complete everything you think about during the weekend. Why Monday 20 hours 8 p.m. Because I have a full day long, and then I have a tutorial until 8 p.m. But we can meet per Zoom. If you have questions, you are invited to come at the same address. Now, let me conclude with this mechanical actuator. We did a lot of things. But I will tell you, believe me, I will present this. Eventually, you can find one of these two possible exercises. Look, this could be an interesting scheme which we discussed. This kind of equation, you can find everything in the data sheet. I don't know if I upload the data sheet. Let me see. Let me stop a little bit. What you can find in the data sheet. You can find the data sheet as in the lecture, everything which you need to solve or to answer the question. Here in particular, you can find this equation here. You can find this. This is the second equation here came from the first one. You can find this, which the second one came from this one. I think in the datasheet you can find F1 divided F2 equal A1 divided A2, like here. I don't know if you can find this one, but you can find x2 divided x1 equal A1 divided A2. Do you remember I try to express or to also to clarify what happens in this kind of actually question now. Please pay attention now. Easy question at the beginning. Try to express the dynamic of x2 as a function of the force F1. Look at this. Mx2, the dynamics of x2. What is x2? X2 is the displacement, the position of the mass M2 related to the fluid which is moving, let me say, on the right part of the actuator. This means M multiplied x2, in which M is this mass here. multiply x2 dot dot, acceleration, gymnasium, equals F2, the force acting on this mass here, minus, I will give you, of course, it's written here, no? Ks, which is the spring, the stiffness constant, or the spring constant. Multiply x2. You remember how in the lecture, how does the spring react? No? Now, using this equation here, excuse me, this equation here, which came from this, I don't know if I put in this formula if 1 divided F2 equal A1 divided A2, but it doesn't matter as I put. If the question is, please express the dynamics 2 as a function of F1, this means you have to calculate F1 as a function of F2, excuse me, as a function of F1, because this expression here is the dynamics of x2, but as a function of F2. But the force F1 is the force which comes from an external structure, typically could be also in a linear motor, which we have seen until now, but could be also in the piezo system and so on. But we have this expression here ready. This is the dynamic of x2 as an this is the dynamic of x2 as a function of f1, which is our external, let me say, input. Again, this f1 could be generated by a linear motor, can be generated piezo or different systems. The dynamic of x2 as a function of f1. But if you look about this expression here, you remember these expressions hold in case the fluid is incompressible. This is very important. In the lecture you can find in the text of the exam I will write the fluid must be incompressible. Therefore, we have these equations here. Second possible question. Right. The dynamics of x1, of course, in this sense, as a function of f1, no? Because f1 is our cause, is our input. In one slide in the lecture, we had mistakes, but now I uploaded the corrected because it was in the old file with the students correct it later and so on. But look at this now. Again, the question: describe the dynamic of x1 again as a function of f1. Why it is a little bit more difficult? Look at this. M, the mass is the same. Huh? The mass which is moving on the part 1, displacement x1, is the same like this. It's incompressible. The mass is the same. Of course, could be not the same if you have two different liquids, but this is more complex. We didn't do with membranes here, pistons with, but consider the same. Excuse me, m multiply x1 dot dot as before, but here we have x1 because the question is the dynamic of x1. F1 should not be changed because very often we write everything in terms of F1 because it's the input. Look at this now. Ks, which must be multiplied by x1. Let me see, excuse me, I'm saying something wrong. No, excuse me, stupid. Ks is here. And Ks must be multiplied, because I made mistakes in the, I would like to say different. Ks must be multiplied by the displacement which we have here. As before, no? think about. But the displacement which you have here, if you remember what I told you during the semester, is larger than the displacement that you have here, which is the goal to have, let me say, such kind of system. I don't know if you can yeah. Why is this one? Yeah, because we amplify the distance. I mean, A1 multiply A2 is the factor, the amplification factor. No? But here I have to write then the force will react against the movement. X2 is A1 divided A2 multiplied X1. A little bit difficult to be understood. I will repeat it. Therefore, we have this square element, which is very strong. It's a very strong reaction in this sense. How to I can try. This spring is acting on the second surface, A2. But the movement of this spring is amplified by A1 divided A2. Remember, large force in the surface 1, small force, or the big force on the A1, small force on A2. But for the contrary, we have probably have I have another slide to clarify better this. Let me see if I have it. In the lecture, you can find probably better both. Yeah, you can find this material. Which is better. Look at this. This balance here. You can find in I will upload also this. I will upload also this. Everything. The energy of the left equal the energy on the right. This means the energy on A1, let me say, or the section 1 equal the energy of the section 2. This means large F1, this is the goal, no? Small x1, small f2, large x2. To be more precise, here should be considered x2, no, where is it? Here, x2 tilde. Do you remember I told you in the lecture? And x2 tilde is this one. because I will move here, I will move here, and the reaction, I move a large element, x2 tilde, but x2 tilde is equal to this one. Because this reaction F2 is amplified. Let me, probably I can comment, I have something red now to comment this in order to understand. I call the F2, right? No, I don't see. Fx, yeah, Fx equals minus F2. No, I'm not right. No, I have no problem. Fx. Mhm. Now, if this is the Fx acting on the surface, I have to, let me say, calculate this reaction here. But this reaction is amplified. Again, small force here, large force here. Large force here, small force here. Therefore, I have to multiply again by A1, A2, multiply x1. And then we have everything on the A1 part. Let me see if I forgot to say something. Okay, I think we can conclude here. I will upload the material of today, also other materials, but other materials is I think is already there. No, many things. I don't know if it's everything, but in YouTube you can find everything also. But I upload many things. I upload many things. You can find extracts. No? Now you can find the folder tutorial. No? We will see. We will see. If you have questions, of course, please send me an email because I will be there until 9 p.m. I'm not sure. I mean, until 9 p.m. I'm there. But if you come, I wait for you. Send me an email if you want to. But anyway, I will inform everybody per my style. Nevertheless, I think now is the time for lunch. But if you have a couple of questions, I can answer you. Otherwise, I upload in YouTube. This very important to look again if you want to refresh. I will upload the material tutorial which we did today. We will look if I can upload also other materials, but more or less it's the same. I will classify with extract one, extract two. You can recognize. You can see that I tried to organize the folder a little bit. Yeah, with different denominations. I hope that you can find what you need. Very important. I upload now the Formelsammlung, the data sheet. If you have question, I'm here. Let me close now the lecture, but I am here for you. Thank you, nevertheless, for attending this classes of this tutorial. Thank you. I'm here for questions.